Almost there. Okay, good morning, everyone. Sorry for the delay. Just trying to get the iPad to work. Okay, just a few things before we get started. Sorry about last Monday. I was recording my lecture on the iPad, and it turned out there is an audio problem. Keep switching between the iPad and the machine here. So instead, I added a video from last year, last spring, on there. Okay, and also for Wednesday, we have the SVM, so we had that lecture from last year as well. And today we'll talk about ANN. For homework number 1, I received a couple of questions from students to postpone the deadline, and I said no, because it's the easiest homework, and you can really finish it in a few hours. And I just want kind of to, hopefully remind everybody to start on the homework as soon as we post it. Because it can be really long. So let's see how homework 2, behaves with you all, and see how things evolve between now and Friday. So today we'll talk about the ANNs, and we'll just start to get into, a little bit of what a neural network is, a little bit of the back propagation, the optimization to some extent. But within the very simple classification scenario. And then on Wednesday, then I will talk about performance evaluation, which is really the last question in your homework, homework number 2. But that will take maybe 20 minutes, 25 minutes, and then for the remaining of the lecture, I really want to go back to classification and just give you kind of an overview, like, have everything that we covered in classification, and start to see how things are connected to each other, because there are certain conditions we impose where basically kind of like with the softmax activation, for example, how that really relates to the regression problem. And then hopefully I will be able to finish that on Wednesday. And then next week we start the second chapter on regression. We'll do regression next Monday. Any question about the plan? Okay, let's get to it. Let me just double check if somebody can hear me. Okay, all right, good. Not seeing anything anymore. Okay. Okay, continuing with the classification. So again, as I mentioned before, decision trees is the only topic in here that I just put it there as FYI, but we will not really go through it. We didn't go through it. And then today we'll talk about ANNs, and it's just kind of introduction. What is the activation function, SLP and MLP, and then look into kind of some of the backpropagation algorithm. Okay, so all of us kind of heard this before. Where we have a biological neuron, it adds in a certain way where there are quite a bit of number of inputs to it, and then there is some operation that's a nonlinear operation, and then there is an output. And the output basically it kind of if the output is above a certain threshold, then basically there is a signal output, and that threshold is like in a voltage fashion. So this is kind of an example in here where you have a certain like number of spikes out of a single neuron in this case. And there we have like billions of neurons, 100 billion plus or minus. And basically that's the idea in here. Basically you have quite a bit of inputs. There is some operation as nonlinear, and then there is an output. And that's basically where the activation comes into play. So one way to kind of to model that is to have this kind of symbol in here that we will see quite often in this semester. So we have, this is the artificial neuron, and then we have inputs. So we have an input data coming in. This is input samples. This is just numbers. Assume just we have a vector. We can vectorize an image. We can vectorize any dimension, multidimensional signal. So we have a vector in here, and then we have the first element in this vector, or first entry. And then we have a weight. So, and then we have a summation. So in this case in here, what we have the weights. We don't have the pen anymore. Okay, I hope you can see my. Okay. So we have the data, multiplied each one of them by the weights. We add them together, we add a bias. And then after that, as we mentioned before, what we have in here is just a linear operation. After it, we have activation. And that's where the linearity comes into play. And there are many different choices of activation. We'll look at some examples in a minute. And then we have an output. And you can imagine basically that's for a single one, then you can have really millions or thousands or tens or a couple of them in your network. So the key words in here are you have inputs, you have an output, you have weights, you have a bias, and then you have the activation function. So now, the input layer in here, we refer to it as layer number 0. So that's number 0. And then the output layer is layer number K. And then we have the ones in the middle. So the ones in the middle in here, these are called hidden layers, right? We could really have just input layer, a single layer of neurons, and then we have outputs, right? So basically, nothing wrong with that. We have input layer, we have an output layer, we have 0 hidden layers, right? And then we have these hidden layers in here, in between. We can have really multiple of them, that's kind of a deep network, or we can have a shallow network where we have only very few of them. What you can see in here, and among these neurons, if you look at this neuron here, each one of these neurons has this operation, right? Weights, add the bias, activation, output, right? So if you notice in here, this neuron is taking every single input, right? This one taking every single input, this one same thing. And here the output of this neuron is really an input to every neuron in the next layer, right? You see that? This neuron output is an input to every neuron in the next layer. And the same thing in here. The output of this neuron is an input to every neuron in the next layer, and so on. So this we call it fully connected. So we have fully connected layer in here, or fully connected networks in this specific example in here. And later on we'll talk about when we don't have fully connected. But for now, we just look at this as a fully connected network. Here are some of the most well-known activation functions, and we already saw the sigmoid function before. Tangent, we have the ReLU, which is a very, very popular one. The leaky ReLU, which is the difference, basically what's happening in the negative direction. Then we have the max and the soft plus. So we'll look at, we'll use some of those examples throughout the semester. For now, we have seen sigmoid and what it means before. Okay. So now let's put some notation. And again, we refer to this as a SLP, which is the single layer perceptron. So now we have a single sample. We have an XI. So this can be the first sample, the first image, the first packet from audio, the first line from a text, whatever the data is. So this is kind of one sample. This is one sample. The easiest to say this is one image, right? And now this is the first element in that sample. So we have X sub I1. That basically means the first data entry or element in data sample I, xi2 all the way to xip. So the dimensionality of this sample is a vector of length p. And then similarly, we have the weights. So we refer to the weights in here as subscript 1 and 1, 1 and 2, all the way to 1 and p. And then we have the superscript, which is between parentheses is 1, to tell us basically which layer we are in this case. And then we have the bias. After that, the output from this operation, this is a linear operation, we refer to it for now as H sub I1. So we can really write HI1 as the product between the weights and the input vector X, where especially it's really a summation, right? So we'll have this as transpose times xi, which is a column vector. So row times column, and they have the same dimension. Then basically we have the first element W11 times xi1 plus W12 times xi2, and so on all the way W1p times xip. And then plus the bias. Output from this activation function is phi in here, small phi, which is operating on the edge. And basically that's the, after activation, our signal is phi. So now a very simple, kind of decision to make is just to make a linear activation, right? Just because, the whole point of having activations is to really impose nonlinearity into the operation. But for now, let's keep it very simple. Say, let's just make it linear, meaning that the output is a binary, and we can decide on the output as 1 if basically the output from here, from our edge is positive, to be -1 if it's negative. And actually it's positive or 0. It will be +1 and -1 if it's negative. Which means basically in here, this one here is just nothing. It's really just linear operation. It doesn't really impose any linearity in this case. Is this operation kind of clear? Okay. So now, if you look at the kind of a visualization of what is this really kind of single layer perceptron is really doing, if you have 2 input, then you have x1 and you have x2, and imagine basically you have the SLP created this kind of line, which is really nothing but W1 times x1 plus W2 times x2 plus the bias. That's all, because you have 2 inputs, right? You have just one x11 and x12, right? And then you have the weights for the first one, the weights for the second one. You have the bias, and basically that's kind of the sign, that's the line you have in here. Why a line? Because we have only two inputs, means that we have a two-dimensional plane, right? So the two-dimensional space, which is a plane. So now you have two inputs, you just need to classify, like a binary classification, you just need a line, right? That's all you need to do. And now, what you see from this visualization, if you have your data basically at this point, that's class A1. If you have this data in here at this point, that's class A2. And then what we have in here, we have this kind of the margin. The dashboard in here, we have this margin. The same thing as an SVM, right? We have this kind of margin around the boundary that is separating the two classes that we are learning. So to learn this model, or what we need to figure out, what will be the values for W1, W2, and B, 3 parameters. Now imagine that we have a three-dimensional or three-dimensional input. So in this case, we have X1, we have X2, and now X2 in here, and then we have X3 in here, right? So our model is W1 times X1 plus W2 times X2 plus W3 times X3 plus B equal to a 0, right? And now that's basically is an equation of basically having this plane, right? It's not a line, right? Because we have a three-dimensional space for X1, X2, and X3. And in this equation here, it's just an equation of a plane, right? And now it depends on which side of this plane, then the point will belong to either X1, X2, or X3. And then when you go to a fourth dimension, we cannot really visualize it, but you can see the idea is you want to create basically kind of a hyperplane in the space, right? When we go to deep networks, we want to create what we call a manifold, right? As a manifold has a certain basically parameters, and for here we have only 3 parameters. For later on we can have 100, 1,000 parameters, or even 1 million. So let's look at the algorithm. How would we, start kind of to operate this single neuron or single layer perceptron? So the first thing we need to decide on, so this is the kind of the learning part of it, right? How do we learn? We have data and we have their classes, right? We know what the output is. We know what the data is. We run them through, right? And then from the output, we can start to figure out what will be the values for W and W, right? And B. So the first thing we're going to do in here, just have an initialization for your weights. So let's say just basically you can just random initialization. And then after that, you will have the output, which is basically, let's say in case I'm using sigmoid as my activation, meaning that this function here is a sigmoid. I'm using this function here, sigma. Then my output can be written as the sigmoid of the W times X, W transpose times X, plus B, right? Then that will give me the output. Now, if I know basically for this input what will be the output in here, then I need to start to, every time I have a new data, I need to figure out how I can update my W's, right? Because the W I'm using in here is a W initiated. And then after that, basically now I need to update this W. So this is where we have weights updates. And we have this T plus 1 just to tell you basically which iteration we are in this algorithm. So this one here, we have Wi T plus 1 is equal to the old weight plus some learning rate alpha, and then the data from the previous iteration, and then time some kind of a difference or an error between the two, right? Now, this error is very important. We'll look at that, right? Because this error in here is what we refer to as the cost function. And then, as far as basically I'm really kind of trying to minimize this error, that's the whole optimization come into play. Then eventually I will converge to some value where the W basically is optimal or suboptimal. And we'll talk about that basically in so now what we need to decide, we need some data that have the class output. We have the inputs, right? We don't know anything about W and B yet. And then we have some kind of an update rule, right? A learning rule in here that depends on the cost function or the loss function. And then we use the Y and the X to keep updating the W's and the B's for many different samples. So that's why more data means we can really have a better convergence. But I really want to put that under, too many, underline in that sentence, because there's an issue with just more data is better. Yes. It's a practice. Basically, there are different rules, basically different ones for this application with this kind of statistics for the data, then use this activation functions. And I'm hoping one of the things we get out of this course is kind of an intuition about these activation functions and when to use them, which applications. Okay, so let's look at this very famous, basically machine learning kind of toy example of the exclusive OR, right? So this is and we call it the exclusive OR problem, which really explains the neural network, the artificial neural network, at least at the SLP level, right? So now we know what an XOR, right? If the two inputs are 0 and 0, or 1 and 1, they are really similar, then the output will be a 0. If they are different, 0, 1, or 1 and 0, then the output is 1, right? That's the XOR. So now, if you plot this on a two-dimensional plane, because we have two inputs, this is x1, this is x2, this is 0 for x1, this is 1 for x1, this is 0 for x2, this is 1 for x2. And now when x1 and x2 are both zeros, then we have a 0. When both of them are 1, we have a 1. When one of them is 0 but the other one is 1, we have a 0. And one of them is 1 but the other, sorry, we have a 1. And if one of them is a 0, the other one is 1, then we have a 1. Now, since this is a two-dimensional plane, and we already know from here, a classifier will be just will be a line, right? So we need to draw a line, right, to classify these two, right? So we cannot really find a line to do this because, they are not really separable, right? Separable. So now, this is where basically the problem is. Whenever you have nonlinearly separable data, then one neuron in here, it cannot really do the job. We cannot really do that job. We cannot really have a one line that can be created by a single neuron to separate basically this output from each other. Does this make sense? Okay. So now that's why we need to go to MLP. We need to have multiple basically layers of these neurons, meaning that we need to get into a network where we have hidden layers, right? So this is basically where we start to really get into, kind of the MLP, where we already know that we need linear activations, and now we need multiple layers, and we'd like to kind of to get into that setup. So the best way to look at this is a kind of a famous example, like a toy example, just to understand what's really happening. So let's really have one step at a time. So let's look at this one. We have two inputs, still x1 and x2, and these inputs can be 0 or 1, so they are digital inputs or discrete inputs. And then instead of really inputting these right away to y, we are adding a hidden layer. So we have a hidden layer. So now we have an input layer, we have an output layer, and now we are adding a hidden layer in between in here. And now for this hidden layer, we have on the left-hand side, we have two inputs. So basically, they will take two inputs each, right? So the first hidden layer in here, we can really use this symbol in here. We have two inputs and output, and then we know basically the W's, or we can pick the W's. For now, just assume that we decide on these W's ourselves. And this W for the first hidden, so WH1, 20 and 20, and the bias is -10. And then the output from H1 will be again the sigmoid of WH1 times X1 and X2 plus the bias. For the second hidden layer, the one in the blue in here, we have the W's as -20 and -20. The bias is 30. And then we have the output from it. This one here is with this operation from the sigmoid using these W's and bias. And finally, for the output layer, we have this W, we have this bias, and the same thing, the output will be a sigmoid function of that. Okay. Now, remember, the input to the last layer are the output from these layers. So basically the inputs in here is out H1 from here, and the second one is out H2 from here, okay? If you put them all together, basically we can really write it in here, and using this setup in here. This is just kind of to split it into different parts so you can really, it becomes clearer to everybody. Okay, so we look at this, we have X1, we have X2, we have weights 20, we have negative 20 weights for the second one, we have 20 weights for the Y, and then we have the biases, negative 30, negative 10, and 30 for this one. And now we have everything, we can really do the calculations. Okay, so now by adding only a single layer in as a hidden layer, so let's look at this. So this is nothing in the upper half of the slide is the same as the lower half from the previous slide. Let's look at this input in here. So we have 0 and 0. So now you know that x1 is 0, x2 is 0. Just run the operations, right? So this is the sigmoid of 20 times 0 plus 20 times 0 minus 10, because that's for the first h1. These are the parameter, 20 and 20, negative 10 for the bias. Then the output of this one is negative 10, so it's approximately 0, because we are here, right? This is the sigmoid function. And now that's only the output from the first H1, from the first hidden neuron. What about the output from the second hidden neuron is sigmoid of negative 20 times 0, negative 20 times 0 plus 30. And that basically will give you 30. So this is clearly very close to 1 in here. And then I have a 0 and 1 output. I input that into the output neuron. Again, 20 times 0, this 0 from this one here, plus 20 times 1, this one from here, minus 30, because I have a bias in here is negative 30. And then that will give me a sigma of 20 minus 30 is negative 10. So basically the output is 0. Again, and I do the same thing for when I have the input 1 and 1, I get an output of a 0. When I have a 0 and 1, the output is 1. When I have 1 and 0, I have the output as 1, and so on. So now what you see in here, we get the table that we wanted, right? Within one neuron, we could not really get the exclusive OR to work, right? But now with just a single hidden layer in between the input layer and the output layer, we get what we wanted. When you have the inputs are similar, we get a 0 output. When they are different, we get a 1 in the output. And basically, you can really look at more kind of logical modeling of what's really happening. And then you can really look at the first hidden layer, H1, as the logical OR function, the second hidden layer as a flip of the logical OR, then the Y in here as the logical AND. And all together, they can make exclusive OR operation. Any question about this? Okay. So now back to what our model was, right? We have X1, we have X2. We have basically, this is one class, and this two are another class, and we can't really have a separation. But now, with a single hidden layer, we kind of have now basically two boundaries, right? Now we have two lines. So now we have two lines that can come separate the planes, separate the two-dimensional plane that we have. So we have these two lines. One line is being learned or imposed by the first hidden layer, and the second one by the second hidden layer. And now we can really have a separation of these. So these two belong to the same class, and these two in here belong to the same class, right? And I can imagine you having, another neuron. Then we'll have another line, and so on. When you have another hidden layer, then basically the operation will be more complicated than just a simple gate operation. Okay. These are some definitions. I will not really get into the math of this to prove these, but this is kind of a theory that's really proven that if you have a single hidden layer, it can represent any bounded continuous function and any Boolean function. But definitely there is a requirement that for every 1,000 inputs, you need 2 to the 1,000 hidden units. That's why you see basically kind of there is a deep network growth, but we'll worry about those later on. Any questions so far? Are we clear? Okay, good. Now let's look at what are, since we are getting, by adding only one hidden layer, we are gaining basically a better model, right? We are having a better capability, right? So what is the price? What are we paying in return? Right? There has to be a cost for that, a price for that. And this is the price. The price is basically the complexity of the model, how many parameters you need to solve for, right? So what you can think of, if we have a fully connected layer as an example, and then you have 3 inputs, the first hidden layer has 4 neurons, the second hidden layer has 4 neurons, and then you have 2 neurons in the output layer, right? So now what we have 4 plus 4 plus 2 neurons, so we have 10 of them. So we have 10 neurons in this case, right? And now how many weights do we have, right? For here, how many weights do we have? We have 3 of them, right? And we have 4 neurons. That means 3 times 4 for this, from this operation here, right? From this operation here, we have 4 and 4. So we have 4 times 4. From this operation here, we have 4 times 2 weights. So we have 36 weights that we need to calculate. So these are 36 numbers we need to calculate. And then how many biases? Then we have 4 in here, we have 4 in here, and then we have 2. We have 10 biases. Right? So now what we have 56 plus 10, that's 46 parameters that we need to learn. So now we have a complex system, right? As opposed to if I just have a single neuron, then all what I need to worry about is just basically a W and a B, right? 2 numbers. And then now there are 2 parameters that will add to this complexity. Adding more neurons in each layer, right, will make these numbers go up. Adding more layers will make these numbers go up, right? Because actually that multiplier effect when you do that. Okay, let's now look at the optimization part of it. Okay, so now let's take a step backward, and then what we are really looking at mathematically, we are looking at a function, right? Use a model theta that maps the input into outputs, right? So we have, let's say for now, we have feature vectors xi, right? And then we'd like to map these to one of the outputs in the y collection. So now the model theta, the parameters are in the w and the b. And actually the w in here is a matrix where each one of them belong to one of the neurons, but we'll look at that notation later. Now, you remember when the iteration we said, okay, there is a cost or there is an error, right? So now, if you guess w, just make a guess for any w and b, right? Just give a guess, right? Then you will have a calculation for y, right? You will have y. So now you need to figure out how good that y is. So you compare the ground truth y and your calculated y, right? And now basically that's kind of what we refer to as the loss function, L of theta, right? Y is a function of theta because that's the model, that's really a function of w and b. And if I have these, then I can calculate what will be my prediction of the output, or what we call it in here, y hat. So the predicted y's and the original y's in here, they are basically compared with each other using a loss function. Now, our job is, in the optimization part of the algorithm, is to find the optimal theta star, that minimize this loss function, meaning minimize the difference between y and y hat. Right? Now, if you want to look at this in a very simple calculus terms, then we take the derivative of the loss function with respect to the model theta. We'd like that derivative to be equal to a 0, right? Basically, that's what we are after. So if you have a convex, basically, loss function L of theta in here, derivative in here is positive, is in here is negative. What we are really interested in this basically derivative, and that when we have a derivative equal to a 0, that will give us basically the optimal theta here. That will be theta star in here. So now how do we do that? How do we find? That's where the back propagation and gradient descent come into play. Right? So let's look at, before we do that, let's just refresh ourselves with some of the calculus derivatives. Okay. So now the derivative of function of f of theta, it tells us the rate of change, how fast, right? Slow or fast or no change. So now that means f will increase or decrease if we change theta. then basically if we calculate for a certain W, we get a theta, and then now we have to kind of compare that, the y hat with the y, and see, do we need to make the y smaller or larger, the y hat smaller or larger? And then we go back and do the W updates, okay? Now, the gradient descent, we have this gradient, basically partial derivatives. That's the initial loss. And then what we are really trying to do, we are really trying kind of to take gradient descent steps. We like to take steps toward the optimal, right? So we have small steps, as in here, or they can be very big steps, right? And I mentioned before, if you have very large learning rate, then you may really skip over, and you have oscillation. And we'll look at some of those examples later on. But for now, just this kind of gradient descent steps. And then every time what you're hoping for, you are converging to the optimal solution and give you basically the minimum loss in here. In most cases, will not be a zero, but will be very small. And you will have some criteria to stop the iteration after the error is below a certain threshold. Okay. So now look at the derivatives in here. So partial derivative of f with respect to theta, and remember, f basically has another function nested in it, right? So we have f of g of theta. That will be simply the partial derivative of f with respect to g times the partial derivative of g with respect to theta. So we have the chain rule in here. So remember the chain rule because it gives us really very important sigmoid property. The next one is the derivative of the sum. So the partial derivative of the sum of fi's is the sum of the partial derivative of the fi's, right? And finally, when we have a function that has more than one element, and then we are really taking the partial derivative with respect to a single element. So this is theta k. That means I'm just looking at one of the thetas, not all the thetas, right? Remember, in here we're looking at all the theta, right? The entire space. And here we're just looking at one element. That actually will result in collapsing the sum because there is no sum anymore because we are just looking at one theta. So in this case, we'll have ak, the ai become ak, partial derivative of the f of theta k with respect to theta k. Right? So these are the kind of three things that from derivatives I would like you to kind of to be refreshed with. And now, any question about these? Yes. Yeah, I mean, this is just a general example. So as you change theta, the loss function will change in a certain way, right? So but what we want the loss function to be as small as possible. Our job is this, to minimize the loss. Oh yeah, this is just a toy example. Yeah, this is just only a toy example. Yeah, this is only a toy example. Just to illustrate how the gradient descent work, right? So you can imagine I just started with W and B as kind of random. I am here. And then if we are really doing the training right and the optimization right, then the next step, we are here and we are really converging to the solution, right? But there will be cases where we are doing some mistakes, and you will do that in the homeworks, where you're not converging. Basically, the loss function just, explode. Yeah, theta is the model. So theta is just a model, but it's really a W and B, right? And W and B, it depends on how many layers you have, right? So in this case, we have W's in here, we have W's in here, we have W's in here, right? And then we have B and B and B, right? For each one of these neurons, right? So now later on we'll make W as a matrix, like a very big matrix, and the same thing for B as a vector, okay? We are taking just a step at a time because I don't want to just dump very complicated deep network now. Very good question. Theta is just our notation of the model. But in the calculations, when we do it's just the way we are naming the model is theta, right? But in reality, if you do the coding or the math, all what we are dealing with is W and B, right? W and B together define the model. We give the model basically theta. And instead of writing I mean, one of the main things that we do, because we are lazy not to do f sub w and b, we just say theta. Just will be cleaner and easier. But really, theta is just a model name. But the real numbers are w and b. Does that make sense? We will do that in a minute. Yes, we will look at how we do that. Yes.
Are we assuming that the loss function, the derivative is the minimum? Like, what if
we assume it's a convex function for now. But in reality, when you have data, it's not a convex function. Or we try to make it a convex function. We like to work with, if it's not, we make it a convex function. So, it will be easier. Okay. Before I go to the steps to do the optimization, I just want to kind of use this toy example. So now we have 3 inputs. We have 2 neurons in here, 2 neurons in here. We have another 3, and then we have another one here. Okay. So now, when we are optimizing, okay, what are we really trying to do? We have the data, we do all the calculations, we have sigmoids everywhere, we have the output y, and now what we are really doing, we are trying to look at the error, which is y. This is the ground truth. This is the ground truth that we have, minus the y that we calculated, right? I referred to as y hat before, but it's y star here. It should be y hat. But this is the difference between the y that I calculated or predicted and the ground truth y, right? And that becomes my error. And now, at every single step in this network, what I'm calculating, I'm trying to minimize the error. So I'm taking the partial derivative of E, for example, with respect to Gj. I'm taking the partial derivative of E with respect to Ugk, right? In here, for example. So every time I'm doing that, as I'm back propagating, I keep updating the weights until I go all the way to the first layer, right? That's the back propagation coming into play. And now as I'm back propagating, then I'm updating the W's and the B's every time, right? And now I have a new W's and B's, run again, and then a back propagation, and I keep doing that, right? Of course, we do it in a parallel fashion, but this is just a toy example for now. Okay, let's look at, before I talk about that, let's just look at this very specific example. Okay, so look at the first bullet. The error, this is the mean square, is y minus y hat squared divided by 2. The mean square error, right? So now, the first thing I want to do, I want to take the partial derivative of this error with respect to the hi, right? Why? Because this is when I'm back propagating, the first things I need to worry about are these, right? These are the inputs to the y, right? So now, that will be what? That will be 2 times 1/2, cancel out, y minus y star, times the partial derivative of y with respect to hi, right? And now, yeah, it's something I missed here. Yes, yeah, I'm sorry, I missed these 2 points. This is a very important one. Let me go back here. If you take the derivative of a sigmoid function, that's the partial derivative with respect to x of 1 over 1 plus e to the negative x, or we just say 1 plus e to the negative x all the way to the power negative 1. That will be minus what I have in the parentheses in here, negative 2, times the partial derivative, what we have inside, which is negative e to the negative x, what I have in here. With basically some operations, I can write it in this form, 1 over 1 plus e to the negative x, and the same thing in here, this term. And if you notice in here, what I have, this is a sigma times 1 minus sigma, right? And this is a very special property of the sigmoid, right? A derivative of a sigmoid is the sigmoid times 1 minus the sigmoid, right? So you can start to see now I have nested fashion, right? I have a nested fashion, and that will become very handy in a minute. And the same thing in here, take the partial derivative of a sigmoid of a function, not an x, but if a function of x, then this will be, again, using this row in here, the sigmoid of the function, 1 minus the sigmoid of the function, but because of the chain rule, I need to take the partial derivative of that function with respect to x, right? and so on, right? And you can see now what that function is, our linear operator, the w times x plus b, right? And we'll see that in a minute. So keep those two things in mind while we're going through the details in here. Okay, let's back to this one. Yes? Yeah.
Why do you only if you're
It's different because it's a function of I. You see? The bias, like for example, this one is a function I0, right?
okay.
And then I have HI, so I have H1 and so on. Keep in mind, in this example here, I have n samples, right? So k in here, just one intermediate. I don't have only 3, by the way. So this is just k is in between. This one is just one of the, so each one of these, like fk, gj, and hi, these are just one neuron in that layer. So the error, the difference square, the mean square error, and then I have the partial derivative of this error with respect to hi, so I'm back propagating. So now what I did, I have my input, I have my initial values for all the b's and the w's I have throughout the whole network. I get an output for y, and now I have a calculation for y. I want to back propagate. So when I'm back propagating, what am I doing? I'm looking at how that value will change, right? If the h changes, right? So now I'm looking to see the relationship between the change in h and the change in the output y, right? So let's look at that. So the partial derivative of e with respect to hi, and hi is just kind of one of the neurons in the last layer before the output layer, it will be y2 times half, cancel out, y minus y star, the partial derivative of y with respect to hi. So I have y minus y star. What is y? Y again is from this operation, right? I have a sigmoid, right? So the y is a sigmoid. And I know from here, the derivative of the sigmoid is the sigmoid times 1 minus the sigmoid, right? So I use that. So now in here, the partial derivative of y with respect to hi is basically the sigmoid y times 1 minus the sigmoid as a y times the partial derivative of that y with respect to hi. What is that? It's just nothing but the w's, right? This is the linear operator. So now the partial derivative of the error with respect to hi is nothing but y minus y hat, y1 minus y, wi. Okay. So now let's take one step back propagation, now one step into the network one more time. Now we look at the partial derivative of E with respect to GJ, right? These neurons, right? Just one of the neurons in here. Let's call it GJ. Not a good choice, but GJ. Okay. So this is same error. 2 times 1 half y minus y star. The partial derivative of y with respect to the GJ. I know that basically the y is the sigmoid. So I have the same thing in here. Sigmoid times 1 minus sigmoid. And now I have to figure out what's the partial derivative of my y in here with respect to the GJ, right? So how do I get that operation? That operation actually is obtained using that linear operation. So now what I need to get is the sum over the i's, wi's, but now I have to remember that rule, the derivative of the sum is the sum of the derivatives. That's what we have, right? So now I have the sum of wi times the partial derivative of the hi's, right, with respect to gj, right? And what is the hi's? This is the equation. Hi is a sigmoid. So now I have another sigmoid. So now I have this term, this term, this term, the sum. I have everything in here, same. I have the wi, same. But this one, hi is a sigmoid. So I know that is a sigmoid times a 1 minus a sigmoid times the partial derivative of the hi with respect, so the sigmoid, 1 minus sigmoid, times the partial derivative of the hi with respect to the gj. What is that? This is vij. I have vij. Okay? And now, what you need to see, basically what's happening in here, I want to compare this term with this term, right? So this term in here is exactly the one I have in here, right? W, right? Was not in here. Basically, we have kind of the sum, and we have this terms in here. You start to see I am start to have this nesting, pattern. So I could write this term in here as bring the sum I outside. I have the hi, 1 minus hi. I have the vij, and then what I have in here is nothing but what? The partial derivative of the error with respect to the hi from the previous layer, right? This one here. You can see as you are really calculating the partial derivative in one layer, you are using it basically to the next layer, and you are really adding, and you are keeping doing that for the next stage. So the same thing in here. I think the partial derivative of the error with respect to the u, because we are back propagating, so this is the next one. And then the same thing. You can really do this again, same operation that we did before. And you can get this very long line here as the result, right? And you can really write this as simply as sum gi times 1 minus gj times 1 minus gj fk, and then the partial derivative of e with respect to gj, which is this one here, right? So you can replace it with this, and then you start to see I'm updating the values in here. I'm looking at how the change of the error with respect to the u, and then part of that is how the change in v, how the change in h, and so on. You see how the nested operation having the back propagation? And that's basically what we have in here. Questions? Each one of them is simple operation, but when they come together, it becomes a little bit confusing. But I hope it's not as confusing. Any question? Yes? Exactly. That's the whole point. And that's exactly where we are doing this. Okay? Now, so what we are looking at this kind of now, we are trying to do some kind of training, right? So we have another terminology, feed-forward propagation and back propagation error. So the feed-forward, basically we have the input samples from the left. The feed-forward, you get an output y. That's your prediction, right? And then you start to compute the back propagation error e, which is the cost function or loss function between the predicted y and the original y, the ground truth y. And then you start to back propagate, and you are usually the chain rule to computing basically all these partial derivatives in here. After doing all of that, now you want to update, right? So now you have all of that. Now you know how the change in the error happens if you change u, if you change v, if you change w, right? So I need to update these weights. Now I go back, I look at my u's, right? So the next step, let's say t+1 step or iteration, I look at the ujk, I use the same value from the previous iteration, and now I need to update it with this gradient, right? So I have a learning rate, and I have the gradient that I calculated in the previous step, which is the partial derivative of e with respect to the ugk, right? And now I have an updated u, and if I have an updated u, then g will be updated, and so on. You see that? And that basically will back propagation will update all these weights throughout the whole network. Okay? Any questions? So we'll keep doing this by hand or by code for the next maybe 4 or 5 weeks or so. And then once things start to become very ugly and it's no way we can do it, then we can say, okay, PyTorch does it in one line. We'll just use PyTorch, one line, it does all that by itself. But for now, I really want to emphasize the intuition behind this backpropagation business. And we look at this from regression point of view, classification point of view, and so on. Okay. So now, for terminology, because sometimes I think in the homework we use these terminologies, and please just ask questions on Piazza. And I really like to encourage all of you to answer each other questions. That's the whole point of Piazza. It's not for us or you actually to answer all the questions. I told him to hold off a little bit, not to answer immediately. I'm sorry for that, guys, but I really want others to answer before he answers. And I hope he will not hold off more than 1 hour, but just please answer each other. Yes.
In the backward propagation, do we assume a sigmoid activation even if we didn't use sigmoid? Or like, what if we use a different activation function?
Oh, then it has to be different. Yeah, of course, yes. In this toy example, very good question. These neurons are using the activation function sigmoid. But if you have other ones, and that actually with the optimization course, basically, you have some other optimization, basically, kind of techniques to worry about when you have different activations. And that's the beauty of PyTorch. We do all that in one line. Okay. So forward propagation is going from left to right, from input to the output. Back propagation, you have now the output that you predicted and the original output or the ground truth output. You have an error, and you are back propagating the error to update the weights. So these are two terminologies that we would like to emphasize. What's happening at every single neuron case? In the forward propagation, we have the inputs, we have the weights, we sum, we eliminate the bias, but you have the bias as well. You have the second part of the neuron, the activation function, you have the output. In the back propagation, you have the error, right? You back propagate it, and then you update the weights. And now you have these updates of the weights. And this symbol will not worry about it for now. Okay. And this is basically kind of another look at it. Okay. Before we, questions? Okay. Now, let's look at this. When you have this network, and again, this is a toy example, we have a multi-class problem. And then we have three outputs, right? We have, let's assume basically we have outputs from, some one round as 3.2, 5.1, negative 1.7. What we usually do, like these are unbounded, right? I mean, it doesn't really tell you much. You have one of them is the ground truth, right? If it's this one here, you don't have that kind of a probabilistic kind of view of what's really happening. So what we do, we bring the softmax. With the softmax, what we would like to do, we would like to look at the outputs in here as basically probability distribution, right? So they sum to 1, right? And now we'd like kind of to convert them from these raw outputs to probability distribution. What we do, we really have the e to the power y, which is e to the power 3.2 or 5.1 negative 1.7. That's what I have here, right? And then we normalize. Basically, we have e to the y's divided by the sum of e to the y's, right? So basically, exponential have these values, and then 24.5 divided by the sum, 164 divided by the sum, 0.18 divided by the sum. And now I have these probabilities for the outputs, prediction outputs. This is 0.13, 0.87, and this is almost a 0. So in this case in here, I have probability distribution. And now that's what we call softmax, basically, activations in this case. Now, when I do the back propagation, it's the same as before, but now I have the hot vector, right? So the ground truth, this is the prediction or the probability calculated from one round, 0.13, 0.87, 0. My hot vector, which is the ground truth, this is for a multi-class problem, multi-classification, right? So one of them will be the class, right? One of them. So the ground truth is, this is the first one, should be 1. The others are zeros. Now, this is the ground truth, right? A hot vector of where a hot vector means only one element is 1, the rest are zeros, right? And then I have the probabilities. And now I can really compare these with each other, right? Start to compare. So now the error, the difference between these two, and then I can propagate this error backward. Does this make sense? And you will have it in your homework, basically. You do it without softmax, and then you do it with the softmax, because now it's much more interpretable, because now you can start to see basically you are really comparing apple with apples. Otherwise, if it's really unbounded like this, how do you compare this with the hot vector, right? Okay. How do you calculate the error in that case? So now let's look at the example where we have an image classification problem, right? So you have an image as an input, and you would like to classify that image, right? So now we have This is kind of the entire model. What is the capital X? This is the matrix of size n times p. That means I have n samples. Each one of them is represented using a feature vector of length p. And now, what is p? Is the number of pixels or features. What is y? Is basically the probability for different categories, right? Depends on how many categories we have. This is the activation function. This is the weight matrix. And b is the bias vector. And we saw this before, right? You take an image, you vectorize it, right? So this becomes 32 times 32 times 3. There's the dimension. You have the weights as a matrix, right? And then you have the bias, and then now you have the output. And again, you can see in here this add to 1, right? Because we use the softmax. So this 0.8 or 0.2, we had the hot vector in here, like let's say 1 and 2. Then we know basically 0.8 minus 1, 0.2 minus 0, and we backpropagate that. Okay. Again, we'll keep using this example again and again until you get to do it. So some samples, yes?
So in that example, we didn't need. So in what cases would we need?
Oh, we did use the softmax in this case, but I'm not showing it in here.
Oh, okay.
Yeah, I'm not showing it in here. Just like an example of how things will look like as a setup. But yes, we did the softmax. And now, it's kind of introducing, every now and then we'll introduce a new subsets or data sets. We introduced this before, the MNIST data sets. These are the handwritten digits, 0 to 9. So we have 10 classes. So this is a multi-class problem. 70,000 of these grayscale images. Each one of them is 28 by 28 pixels. In the data set itself, there's a split, the split between training and testing. So 60,000 images are used for training and 10,000 for testing. Why? Because it's very important in literature when you have, research and papers on the MNIST to really compare apples with apples. If everybody pick their own testing data split, it's not really fair, right? So that's why datasets will have their own split coming with them in here. Now, it's very simple, right? It's a grayscale, very simple images. We use MNIST as a toy example. I don't like to see papers that use MNIST to convince of an idea because you can do anything with MNIST to satisfy what you want to do. So let's take it a little bit more difficult. So this is a Cipher 10. Again, it really came out from literally extrapolation of the MNIST, but with more complex images. So we have 60,000 color images that are taken from 80 million tiny images. Again, same thing, 10 classes, very close size, 32 by 32. The split is 50,000 versus 10,000 for testing. These are the images, and I use those in the classification first. This is the one I use, right? At the beginning of the presentations. So these are the classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, truck. And you can see the images are not as simple as MNIST, but also they are not really as complex as real life, right? Why? Because the background is very simple. You have a single object in the image. The background is very simple. So it can be very good for classification and for recognition as well. So these are kind of the data set. Let me go back to that slide. Okay. So the next thing we'll do on Wednesday, as I mentioned before, I'll go through performance evaluation. I'll go through all of this. I'm hoping to finish all of this in 20 minutes, 25 minutes, and then I'll spend 1 hour, what the calculations are, less 55 minutes, on kind of the classification from a very 30,000 feet kind of view, and connecting things together, SVM with the regression, logistic regression together with the ANNs. And you will see basically they are really very related, especially when we bring the softmax into the equation. Okay, any questions? Any feedback so far? Any comments? Is the speed okay? Maybe. Yeah, we are taking off a little bit by little, so I think it will be a nice ride. Right, we'll see you Wednesday, guys. Thank you.
a question about this.